All right, cool. You're good to go, no? Okay, final talk for today. With Altman, Symmetry enriched phases of quantum circuits. Go ahead.
So thank you very much for inviting me to this conference. Sorry that I have to miss all the early talks. They look great. I'll look at them after. So this is work I did with Yimu Bao. It's a fantastic student in Berkeley, and Sunwon Choi, a Miller postdoc, who's moving to a faculty position in MIT. And this deals with phases, basically looking at quantum circuits as a new type of many-body system and asking the question, what kind of phases of information flow one can have in these systems? And turns out that there is a new, perspective one needs of statistical mechanics in order to understand these phases because of the special role played by information. And a lot of them, I'm going to keep the introduction a bit brief, but a lot of this is motivated by the fact that there are new platforms for processing quantum information that build these beautiful circuits. Like example is the experiment by Google of quantum supremacy. I'm not going to talk about this experiment in particular, but it's an example of a intricate quantum circuit that one can have. And we also see examples of quantum circuits in other platforms like ion traps and Rydberg atoms and ultra-cold atoms. And again, my focus today would be to talk about these systems or quantum circuits in general as new paradigms for quantum many-body physics. And an example of how it can be a new paradigm and what is really different is this measurement-induced phase transitions in hybrid quantum circuits. So first of all, what is a hybrid quantum circuit? It's a circuit that includes the two fundamental time evolutions we know in quantum mechanics when you learn it in undergrad, which are the unitary evolution implemented by quantum gates here. These are the blue squares, and quantum measurements that can be done along the way. And in the simplest case, these quantum measurements are simply projective measurements. So you basically measure, in this example, it doesn't have to be a single qubit measurement. In this example, I draw single qubit measurements where you have a measurement device, and according to the Born rules, it collapses the wave function by projecting it into one of the eigenstates of the measurement operators and then renormalizing the state. So these are the two most fundamental evolutions of a quantum state. If you start with a pure state, this evolution will keep you in a pure state, okay? And it's important to understand that in all of this, what we have in mind is an ensemble of quantum trajectories. And we have some access, we assume that we have access to individual quantum trajectories. A particular quantum trajectory corresponds to a sequence of measurement outcomes in all of these measurements along time, right? So it's like a tree of different possible trajectories, and we're sort of generating in this circuit such an ensemble of states, and then asking a question like, what is the entanglement entropy of a trajectory state like that? So such a pure state has an entanglement entropy, say in a subsystem A, and we ask, what is the average over the ensemble of trajectories of this entanglement entropy A, okay? Note, it's an entanglement entropy in this case of a pure state, if the initial state is pure. And the result of these numerical papers and some analytical arguments is that there is a phase transition as a function of the measurement rate. So if you had no measurements, this would be just a unitary circuit with random, if you have random unitaries, they would generically make the entanglement grow linearly in time until it saturates for a subsystem of size A to a volume law proportional to the volume of the system A. now when you start measuring, if I had only measurements, then I would immediately collapse the wave function to a non-entangled state if the measurements are completely local. But now there is some kind of competition that I'll talk about, and it gives rise to a phase transition at PC, at a critical rate of measurement, where the entanglement entropy density goes to 0. So, there is a little bit more, it's a little bit more interesting. It's not just a competition between measurement that disentangles and unitary that entangle. The real competition here, it turns out, and what makes the volume law phase stable and not collapse immediately to any kind of small measurement rate is this robustness has to do with error correction. Basically, the unitary evolution scrambles the quantum information, and by scrambling it, what it means, it encodes quantum information into highly non-local degrees of freedom that are hard to measure. So if we try to measure it with local measurements, we reveal nearly zero information, and therefore we are not completely collapsing the state, and we have some remnant logical qubits, and this is this entanglement density. It's the number of logical qubits that propagate in the system coherently. So this is basically the volume law phase is sort of an emergent error correcting code. This was pointed out in these papers. Okay, but in this talk, I want to, as I said, to think of this hybrid quantum circuit with unitary and measurements, unitary evolution measurements, as generating some kind of a new kind of ensemble of quantum trajectories. So basically, to analyze this ensemble, we need some kind of statistical mechanics, but it's very different ensemble from the thermal ensemble. It's also different from a quantum ground state. So it's also different from the quantum ensemble. And in this sense, there is an interesting new element here for many-body physics and statistical mechanics. And the question is basically how to characterize this ensemble theoretically and experimentally, and what are the possible phases of this ensemble of the circuit. And as any, physical system, we can ask, how do we classify these phases based on the symmetries of the problem of the circuit, for example. So this is the main thing I want to ask in this talk today. So what I'll show is, in order to simplify this classification, I'll show that a lot of pertinent properties of this ensemble can be mapped to ground state of an effective Hamiltonian. So this complicated dynamical problem, at least for a certain class of circuits, can be mapped to a ground state problem with an effective Hamiltonian. But this effective Hamiltonian operates on a larger dimensional Hilbert space and has an enlarged symmetry compared to the immediate physical symmetry imposed on the circuit elements. So that means that the kind of phases we can get are unexpected or would not be allowed based on just the physical symmetries of the circuit alone. That's basically the main takeaway. But now let me go into a bit more detail. How do we characterize the ensemble of trajectories? So, the easiest thing would be, well, we want to measure expectation values of observables. The problem is that if measuring expectation values of observables means summing over all the possible measurement outcomes, or tracing over the measurement outcomes. If we discard the measurement outcomes, trace over them, basically we get a quantum channel, and measurement operators are Hermitian. It means that this channel is unital, and what we get is that in steady state, the average density matrix is essentially unity. So all the expectation values of operators are basically trivial. They're what they would be in infinite temperature. So there is no interest really in this average of observables. what we really need to consider, we want access to individual trajectories. So the minimum we could do is look at fluctuations between trajectories. So at least we need to look at second moments of operators in this trajectory ensemble, right? The sum over all the measurement outcomes, probability of that particular measurement outcome sequence, and the operator in this particular trajectory state to the power k is the kth moment. Then I have averaging over a random unitary, all the possible network constructions, but this last average is maybe the least fundamental. But the average over measurement outcome is unavoidable and fundamental, of course. Okay, so these moments, if we want to capture moments of these operators, we cannot capture them by the average density matrix, but we can capture them by looking at moments of the density matrix. We can capture the second moment, for example, up to some subtleties that require auxiliary replicas. I'm not going to talk about it now for time. But we can capture it by n copies of the density matrix. So we can capture the nth moment by the n copies of the density matrix propagating on this circuit, and then averaged over the circuit elements. So here is just a representation of this replicated density matrix, and I'm going to use this notation. Basically, instead of looking at this as an operator, we can think about it as a state in a larger dimensional Hilbert space, basically a quadrupled Hilbert space compared to the state Hilbert space. Okay, so this can capture moments, and it can capture Rayleigh entropies and so on. Yeah, I hope it's clear so far. Okay, so now what I said is we can map, I promised you that we can map this dynamics to a ground state problem. So how can this, how is this done? So this is maybe the most technical point here, but let me explain it, try to explain it clearly and in the simplest possible way. So when we calculate the dynamics of, say, a double density matrix, let's look at the double density matrix. It's the simplest case if we want to calculate second moments. So this is the double density matrix. We have to calculate the time evolution with the circuit of the ket, bra, ket, bra. So we have 4 copies of the circuit here, and calculating anything, for example, calculating the entanglement entropy at the end means contracting this tensor network that is built by the time evolution. Of course, that's very, very hard. It's as hard as calculating quantum time evolution. So maybe it's not such a good idea. What really greatly simplifies the problem is the fact that we take the unitary operators to be some random unitaries. In this case, I'm going to take the unitaries to be Brownian, basically. So they're going to be generated by a local Hamiltonian with random parameters that change from side to side and from time to time. And then averaging over them is easy. We have, if these are Gaussian variables, we can average over them. The nice thing, if these are Gaussian variables with 0 mean, we get, after averaging over these unitaries, we get an effective term in this tensor network, basically that looks like imaginary time evolution for a small time step. If this is close to unity, if the unitary is close to unity, then we have a small time step, imaginary time evolution with some effective Hamiltonian. This is for averaging over unitaries. If we have measurements, then the measurement projects to the same state in every one of these branches, ket, bra, ket, bra. And so we have all these 4 projectors. But again, if the measurement is at small probability per time step, this thing basically also behaves like an imaginary time evolution of an infinitesimal time step. And we can put these things together, and we basically have that the initial density matrix, which we said we can write as a state in this extended Hilbert space, in this quadrupled Hilbert space, is evolved by imaginary time evolution with an effective Hamiltonian that we can in principle write down, given a model, okay? So for this class of circuits with small Brownian unitaries and symmetric distributions, we get just imaginary time evolution. So we map the problem of this dynamics averaged over these unitaries to a ground state problem, because if we take it to long time evolution, of course, we project onto the ground state. And now, how do we calculate operators? If we want to calculate a certain moment of an operator, we said we need at least second moments. In fact, we really need to do some careful replica limit, which I'm not going to talk about here. But if we really look at, so most generally, this Hamiltonian, effective Hamiltonian creates the ground state. Then to implement a trace, we need to cap this tensor network from the top by some reference state that implements the trace. In this case, it's a simple state like that that has certain properties. And in the end, what all of this maps to is this matrix element of the boundary, and in the boundary of this circuit between the ground state and this reference state with some operator. And the operator acts in this extended Hilbert space of the 2 times 2 copies, or n copies in more generally. In particular, when I want to calculate purity, for example, this operator implements a swap between 2 copies. That's an example, two copies of the system, copy 1 and copy 2 left. There is also a denominator here. The denominator here has to do with the fact that this imaginary time evolution is, of course, not conserving the norm. And this denominator basically renormalizes the state at the end. And of course, this is the problem that requires replicas here. So what are the symmetries of the problem? Before we classify what states we can have, I want to classify the symmetries. And the first symmetry we have, regardless of what is the symmetry imposed on the individual gates and measurements in the circuit, we have a built-in symmetry because of the type of dynamics we have. If the dynamics only includes unitary evolution, right? Unitary evolution evolves each side of the density matrices independently. There is no connection between, there is no interaction between ket and bra due to unitary evolution. And the measurement actually projects ket, bra, all to the same state. So both of these evolutions have this symmetry that you can interchange, you can permute independently the left or the right states, right? So you can either permute the bras or can permute the kets. There is another symmetry that I won't talk about too much here due to conservation of hermiticity of the density matrix, which is related to flipping ket and bra and complex conjugation. Okay, so this symmetry, if I have only this symmetry, basically for a 2 replica model, I map to a system with S2 symmetry. And the 2 degrees of freedom in this S2 symmetry, I can think of them as spin up and down. The spins up and down correspond to swap or no swap. Swap between basically swap and no swap corresponds to when I consider a particular trajectory through unitary, for example, I either pair and identify the 2 copies, the bra and ket from the same copy or from different copies. These are the 2 states in up and down. And there is the entire time evolution maps to an effective Ising model with some maybe more extended interactions. And there is a phase transition as a function of the measurement rate. There is a phase transition between an ordered Ising model and a disordered Ising model. And the ordered Ising model has a finite domain wall free energy associated with a boundary. So sorry, calculating the entropy corresponds to forcing a swap in a certain region, say region A, which means forcing a boundary conditions that these spins have to be down. And that forces a domain wall in the boundary. And if this domain wall costs linear energy in the size, it's a volume law phase. So our Ising ordered phase is a volume law phase, and the Ising disordered phase is the area law. Now let's add actual symmetries to the elements of the circuit. For example, the elements could be invariant under some U1 symmetry, under some Z2 symmetry, and so on. Then actually this symmetry is replicated n times, and when we swap kets or swap bras, we can also swap the elements of these symmetries, and this gives rise to this enlarged symmetry G to the n, where G is the internal symmetry times Sn, G, basically this complicated extended symmetry. It turns out that in many, many cases, one can greatly simplify this symmetry. But this is the symmetry that eventually, or the simplified symmetry that you can simplify due to certain local symmetries that give you more constraints. But then in the end, that's the symmetry that dictates the phase structure and what are the possible phases of the circuit. So just as first example, maybe I won't have time for the second, unfortunately, but at least the first example, I have a qubit circuit with only Z2 symmetry. So here to the right, you see a circuit, and the symmetry generator of a single circuit state is, for example, let's call it parity. It's the product on all the qubits, Zj. So what are the possible circuit elements? Possible elements are single site Z rotations. You can, of course, have also ZZ. I can also have three Zs, three site. So Zs are not restricted, that they commute with this generator, of course. But I can only have even number of X's. So I can have XX terms in my unitary gates. Also in the measurements, I'm allowed to measure a single Z, but I'm only allowed to measure two X's, XX, for example, nearest neighbors. So this is an example of a circuit with Z2 symmetry. So we can ask, what is the enlarged symmetry in this case? So if we take for granted what I wrote generally in the last transparency, it's D4 cross D4 times this Hermitistic Z2 symmetry. But it turns out that in this case, there are a lot of other constraints associated with the fact that we're dealing with Pauli matrices, and the symmetry can be reduced down. The effective symmetry can be reduced down to D4. Basically, this phase structure is dictated by D4 symmetry. And okay, you don't have to look at this table. There is a table of symmetry analysis. What are all the possible phases, and how do we basically translate them to measurable properties in the circuit that distinguishes between these two phases? So you don't have these different phases. So you don't have to look at all of these. But the interesting thing is that there are many more phases that you would expect to be, that would be allowed if your circuit only has, if for a Hamiltonian that only had Z2 symmetry, right? So in particular, we have five different area law phases that are in principle allowed. These include two interesting topological area law phases that are protected by Z2 cross S2 symmetry. So Z2 symmetry alone would not allow in one dimension a symmetry protected topological phase, but here we have this dynamical symmetry, if you want, S2 permutation symmetry, and it binds together with the Z2 symmetry to give you a possibility of these strange topological phases. And they can, in principle, even be detected. We don't have an example where for a concrete model yet, though. And there are also 6 different volume law phases. So it, of course, begs the question whether we can actually demonstrate these phases, these states, in a concrete model to show that we can have more than just what we would expect from Z2 symmetry. So as a warm-up, let's look at a measurement-only model with Z2 symmetry, no unitary gates. How much time do I have?
A little more than 5 minutes, 7 minutes.
Good. So probably at least I'll go through example 1, not example 2. So good. So yeah, let's look at only measurement, a circuit with only measurement. So it's a very simple circuit. You have every line here, basically, you have an input state of qubits, and now you start to measure them. And either you measure just locally the Z, make a Z measurement locally, or you make XX measurements. So now you can have, now this was by the way discussed in this paper by Sang and Shi. And if what dominates are the Z measurements, then you expect to project onto something like that, where the Z is well defined, meaning that the parity is well defined. You have a definite parity state. No long range order if you want, but definite parity. This implies that if I measure this variance of the parity operator on a subsystem A, even in a very long subsystem, it decays to some constant and not 0. So again, the only note that I need to look at not the parity, but the parity squared and average, right? This is the fact that I need to look at moments. So this is what I expect in this Z-dominated phase. I also expect another phase when the XX measurements dominate, where because X measurements do not completely fix X, right? They always either, for example, they can, if XX is positive, it will project you to the state with minus X plus the state with plus X, then you will have dominating configurations that are cat states like that, where you have a broken symmetry state, but it's in some random configuration. So how can you measure that? How can you find that? Well, you need an Edwards-Anderson-like order parameter, right? If you'll just look at the average spin on each site, that will be 0. But if you look at the average spin squared, and because you have this cat state, you really have to measure the correlation function, Edwards-Anderson correlation function. So it's a spin-spin correlation function, then squared, averaged over trajectories. That would be non-zero in this XX-dominated phase. And indeed, that is what you find. You find a sharp phase transition between these two phases. But this is not really surprising. It's actually what you expect from a circuit with Z2 symmetry. You have a symmetric phase and a broken symmetry phase. So far, there are no signatures of the enlarged symmetry that I advertised so much. So can we actually see the enlarged symmetry? So here is a more elaborate model that includes not only measurement and actually includes 2 chains. Chain 1 is just has unitary evolution with unrestricted by symmetry. So there is no symmetry here. Chain 2, on the other hand, is restricted by a Z2 symmetry. So the Z2 parity basically operates only on the blue spins here of chain 2. And we're going to have measurement only here. So if we take these 2 chains alone, chain 1 creates volume law phase. Chain 2 has the phase transition I showed you above between the symmetric and the non-symmetric phase. But now let's couple them with a unitary coupling that respects the Z2 symmetry. Now, in the ground state picture, each one of those chains evolves to an effective ground state, which is gapped. So this small coupling between them should not really change the fact that we have a volume law phase with some order. But at the critical point between the 2 ordered phases, actually it turns out that this coupling is relevant and it opens up a new phase. So that is a phase that would not be expected if you had only Z2 symmetry. In the Z2 symmetric model, the parity operator I showed you, parity variance, and the Edwards-Anderson order parameter are dual to each other, and they're always mutually exclusive, and they appear and disappear at exactly the same point. But because of the larger symmetry in this problem, actually they're not dual to each other really. And because of that, you're allowed to have a phase where you have neither one of them. And so this is this intermediate phase. And in principle, you can also have a phase where both of them exist. And we think we can also realize that phase, but that needs to be seen numerically. So this is a direct demonstration. The fact that by turning on the coupling between the two chains, I can have 3 different volume law phases with different kind of quantum orders, is that we go beyond this just Z2 symmetry. It's also kind of interesting because this is a volume law phase of a one-dimensional system that can sustain long-range order. So it also shows that this is an intrinsically non-equilibrium phase. Such phases with long-range order would not exist in equilibrium, could not exist in equilibrium. Okay, so I think I don't have time for talking about Gaussian fermion circuits. That was my second example of how enlarged symmetry comes into play. So basically, I'll just summarize that phases of hybrid quantum circuits can be classified as ground states of an effective Hamiltonian with enlarged effective symmetry. I've shown you one example of a qubit circuit with Z2 symmetry, and I showed you that phases can be classified by a larger D4 symmetry. And this includes broken symmetry volume law states, which we have demonstrated. And at least in theory, we can have an SPT phase protected by Z2 times a permutation symmetry. And there is a question whether one can actually realize this in a concrete model, or there is another obstruction, fundamental obstruction to realizing it. What I didn't show you, but maybe I can just advertise, is Gaussian fermion circuit. It's a fermion circuit, basically quadratic fermion circuit, where all the measurements and unitaries obey preserve the Gaussianity of the fermion wave function, and we have only Z2 fermion parity in this system. So it's basically can be described by Majorana fermions if you want, no U1 symmetry, but the enlarged symmetry in this case turns out to be, with measurements, it turns out to be a O2 symmetry. Well, I said U1 here, it's O2. At least for a model of double density matrices. In principle, one has to take a replica limit, so it might be more subtle, but at least for this double density matrix model, we have a U1 symmetry, and we have evidence, both numerical and analytical, that there should be a phase transition between a critical phase for weak measurement rates, for small measurement rates, to 2 possible area law phases. One of them is a topological area law phase, and another a non-topological area law phase. And the transition, at least within this 2 replica theory, and it's consistent with our numerics, is a Kosterlitz-Dowless transition. And the surprise is it's a Kosterlitz-Dowless transition, although there is no U1 symmetry in the circuit. The circuit only has Z2 symmetry, but the enlarged symmetry is U1. And there is, the outlook is, I didn't talk too much about the replica limit. We can discuss it a little bit. There is another way to address these fermion circuits, for example, in terms of loop models. And it's interesting to understand whether in all cases, these Gaussian fermion circuits are related to loop models with crossings. And actually, I think in these systems, if I'm not mistaken, it's not completely clear what the replica limit is also. I only showed you systems with Z2 symmetry. How does continuous symmetry behave here? What is the interplay between these information flow and actual hydrodynamics of conserved quantities? The phase transitions I showed you now require us to have knowledge of particular trajectories. And in order to use this knowledge, we have to post-select. And the question is whether we can do something without post-selection. For example, can we trade post-selection to feedback on the system, which is sort of like more active error correction, and in this case, not need to post-select so much. Finally, in these circuits, I only allowed measurements and unitary evolution, but real quantum circuits also have errors, which you can, one way to think about errors is unregistered measurements which you throw away. And how robust are all these things, or whether some of these transitions can be robust to real errors. So that's it. Thank you.
All right. Thank you very much. Thank you. Yeah, we have time for questions until midnight.
I have a question. So is when you consider multiple replicas, is the generalization you want the to ON?
Yeah, so I have it here, right. So the generalization more precisely is this. Oh, sorry, I went over it. Yeah, so at the bottom here. So actually, only unitary dynamics, we have O2N symmetry in case of N replicas. And if we add measurements, that O2N symmetry is reduced to ON cross ON. So rather than O2 cross O2 for 2 replicas, you have ON cross ON. And in reality, you actually need to take the N to 1 limit.
So you still have this kind of transition for N bigger than 2?
That's a good question. It's not so clear. You actually have Z2 vortices for N bigger than 2. And you can have a transition in which Z2 vortices proliferate for N greater than 2. It's very similar to the question in, it's almost the same as Fermion's symplectic in symplectic class. And the difference is that you go from O to N to ON because you have a non-Hermitian term, if you want, that reduces the symmetry. But I think people actually address this kind of symplectic model with exactly the same idea as proliferation of Z2 vortices. And then one needs to take the replica limit. The difference is that in this O to N, you need to take symplectic model, you need to take N to 0. That's a physical replica limit. In our case, you need to take N to 1, but I'm not sure if it's so
Okay.
how meaningful it is.
Subir or Marco, I don't know who was first. I mean, any one of you guys.
Just a general question. What's the implications for all these different phases for quantum computing, or I mean, how would they show up?
Yeah, very. What I would say is that because the kind of errors we have are just measurements and not real errors, it doesn't really reflect robustness to actual errors. And in order to really say how it is related to quantum computing, what I would like to do is to somehow generalize to actual real errors that give rise to a mixed state. The problem is that this actually breaks this SN cross SN symmetry basically by hand if you add these kinds of errors. So I think it's not terribly, I don't know how to make a complete connection. However, I think once you add feedback and allow feedback to correct errors actively, then maybe you restore some of these symmetries, and you can make a connection between threshold theorems and these kinds of thresholds for measurements, which then, and okay, and then there is another thing. Yeah, so then there is another point which I think is related to quantum computing. What we've shown is that you can actually cool the system with measurements, right? So measurements, if you don't look at the measurement results, then you think you're heating the system because they're like noise. But if you actually have access to individual trajectories, then each individual trajectory is cooled by the measurement, especially if your measurement operators are designed, because it projects you to the state you want, or to a class of states you want. So what you can do, for example, is use measurements in order to cool the system into a topological state, which would be another way to stabilize, for example, a surface code. And so I think that maybe would be another direction that would give you connections to actual quantum computing.
But that's measurement-based quantum computing, right? That's an idea that's been around.
Yeah, well, measurement-based quantum computing is actually doing, I'm not sure it's the same thing. So measurement-based quantum computing, you start from some reference state, and yeah, the measurement-based is actually doing the processing. Here, I'm just cooling the system into a state which has anyons, and then I can do really unitary evolution of these anyons. But what I'm doing is cooling the system into a state where the anyons are protected. So although it's a random state, but in every one of these realizations of the trajectories, it's a random state where the anion is protected, for example. So maybe it has some elements of measurement-based quantum computation, but I'm not sure it's exactly the same. You're also not using the measurements as a way to implement some unitary dynamics. There is no underlying unitary dynamics associated with measurements.
Two more and hopefully very quick questions. We are already over time.
Yes, hi, Ehud. A question about this mapping to ground state. I was wondering what are the conditions, because I would imagine that for a two replica kind of vectorized density matrix, in general, you would get an Hermitian Hamiltonian.
Yeah. So good.
Is it because your gates are random?
Yeah, it's just because it's not only that they're random, they have a symmetry from negative to positive. So in this effective Hamiltonian, the coupling constants have a symmetry between around zero.
Okay.
If I didn't have that symmetry, I would have small. Well, it's interesting to understand what would happen, for example, if I made the small perturbation.
Would have an Hermitian Hamiltonian, probably, right?
Yeah, and then I'll have a small non-Hermitian term, and I could probably treat it perturbatively as long as it's small. But it probably will affect the phase transition, because so it's actually a very interesting question what to do, but we wanted to avoid non-Hermitian Hamiltonians.
Okay.
At least at first.
Thanks.
Yeah.
All right, Philip, last question for the day.
Yes, thanks a lot. Hi, Ehud. Just a very quick question, sort of following up from that. So because of this mapping to imaginary time, you basically lose all time structures. We know that, for example, for flow K, there's sort of a dynamical symmetry. Could you still have something like that with your random averaging?
Wait, for K? For which?
Flow K, for a periodic evolution, you get an emergent dynamic symmetry coming from the periodicity. Is that something that could survive your procedure?
No, because, right. No, because I mean, my map is reliant on having random independent in time unitaries. If they were flow K-like, I would generate, of course, infinite couplings in time, and that would be really, much more. It would be a different story. So for example, flow K structure is not possible to at least simply capture in this kind of approach.
So you need the randomness in time in addition to the randomness of
otherwise, right. Otherwise, the averaging would cause, just like in usual replicas, would cause infinite couplings in the time direction. Yeah.
Thanks.
Yeah.
Okay. Cool. So thanks, Ehud, and thanks, Xiaolang, our two speakers for the last session, and see you tomorrow. Marco, do you want to say anything else? Or?
No, I think we'll resume tomorrow 2 p.m. Thank you very much, everyone.
Thanks.